Hello and welcome to this manufacturing process technology part 2 module 33. In the last module we had talked about the various circuits which are associated with the EDM process in general and is able to supply the voltage signal so that there is machining, metal machining that takes place. So, in context with that we had discussed the resistance, capacitance, relaxation circuit in great details. We had also looked into some other circuits like the controlled pulse circuit and the rotary impulse generator circuit, and each of these circuits had an advantage over the other in terms of the advancement in the technology. So, today we are going to look into a little different aspect which is related to the surface finish of an EDM process and how that can be correlated to the various machining parameters which are into picture. So, obviously as you may all recall that the EDM process because it is a spark machining operation and there is always a formation of a melt zone and a crater. Therefore, there is going to be in general high surface roughness associated with this process. So, the challenge is about how to control that by optimizing the spark parameters or the parameters of the machining and be able to produce relatively smoother surfaces. So, let us look at some of the details related to that. So, we talk about surface finishing and machining accuracy. So, as we all know that because the material removal process is really the cratering action and the cratering action always results in a rough surface. So, the important point here is to control the crater size, so control the crater size. And the crater size would depend mainly on the energy per spark, as I think I had illustrated earlier. How you may recall how the depth of the crater Hc was related to the spark energy by some constant times of this energy e to the power of 0.33 in millimeters, and E was the energy applied in joules, and this would be actually the half CVD square, where that would relate to the discharge energy of the capacitor through the discharge circuit of a resistance, capacitance, relaxation circuit of an EDM process. So, this energy really controls the quality of the surface, makes the surface high finish, and the average surface roughness illustrated by the root mean square roughness, which typically depends on the capacitance C. So, as the capacitance increases, the energy is increasing, as you can see here from this relationship, and if the capacitance is more, then obviously the crater depth Hc is going to be more and the surface roughness is going to increase. So, this is the root mean square average roughness HRMS. So, it depends on what is the discharge voltage, okay, and the discharge voltage, as you know, is again dependent on the source voltage. So, discharge voltage typically is 72% of the source voltage. If you may recall what we had done for optimizing the power transfer from the source to the electrode gap, okay, in earlier modules. So, obviously the Vd depends on V0, and so if the V0 is higher, then overall the surface roughness is higher. You can see here the correlation VO3 is one of the source voltages greater than VO2 is greater than VO1. And so, you can see that with an increase in capacitance, again, first of all, even if the capacitance were same, there is going to be a difference in the roughnesses because of the discharge voltage is high value, and if the capacitance is increased, obviously the energy E would further increase by a multiplicative factor here, and which would result in an increase in the crater depth and overall HRMS. So, obviously when we had talked about this empirical formulation here about crater depth, we had assumed this K1 to be a constant depending on the material, and for copper we had stated if the copper is a work material, K1 is approximately to be treated as 4. So, that is how the surface finish part happens. Let us just try to introduce the C and V values here in this equation with a value of K1 for cop. So, if we put the value of the various capacitance and voltage, as you can see here for the energy equation here, it results in another equation where Hc can be represented as this 0.78 k c to the power of 0.33 Vd to the power of 0.66. Obviously, because E as you know is half CVD square, and if we are raising this to 0.33 as is normally the case for the equation on the crater depth. So, this we can call it a general K, because K1 is typically 4 for the purpose of copper material. So, you are not going into only copper. So, okay. So, this becomes equal to K times of half CVD square, or K times of C to the power of 0.33 Vd to the power of 0.66, half to the power of 0.33, which is actually 0.79 or 78, you know. So, this becomes 0.79 K C to the power of 0.33 Vd to the power of 0.66, which is actually what is being represented here. The dependence of the surface finish on pulse energy E and comparison of the surface finish with that obtained by conventional processes are very well studied, and there is also a lot of empirical study done on this as to, you know, if I had some material removal rate, would there be a relationship between that rate and the HRMS. A lot of studies have been made because obviously a critical parameter for all the processes or processing related to any other machining processes is MRR, and the MRR actually would be determinant of what is the spark energy, for example, or what are the other you know, associated mechanisms or parameters for the MRR to have a certain value. So, already there is a good mapping of the NRR into the various other parameters. These parameters could include, for example, the spark energy E, okay, and also maybe the rate at which the feed is given to the system, okay. So, and many other parameters which are related to the EDM process, as we have done earlier in the earlier modules. So, an empirical relationship exists between the MRR and the HRMS, which makes life simpler, because the critical parameter really, which depends on all these, or all these parameters really make the MRR happen at a certain rate. They would necessitate to be changed if you wanted to change the MRR. And certain relationship, an empirical relationship between roughness and MRR exists for steels particularly. And steels, you know, if Q is the MRR in millimeter cube per minute, and the HRMS that we are taking is in micrometers. So, we can empirically relate the HRMS to Q by 1.11 Q to the power of 0.384. Now, if you wanted to have the dielectric fluid force circulated, it is obviously going to create higher material removal rate, because as you are already aware, in case of ECM also the same thing happened, that as the electrolyte was circulated at a higher velocity, the material removal rate would improve. In this case also similar kind of a thing happens, because obviously whatever material has been cratered and melted inside the surface because of the discharge of a spark still remains there and diffusively moves into the electrolyte which is over it, and if flowing this electrolyte or dielectric over it, and flowing this dielectric at a higher velocity would mean faster diffusional process. So, which leads to quick debris removal, and also you know, can increase the spark frequency, because the ion column which has been created would actually disappear more quickly on forced circulation cases. I think we had discussed about these relationships quite a bit. So, let us look at some trends related to the HRMS and some processes. The HRMS for particularly you know, different pulse energies are illustrated here in this example. So, this is the pulse energy in joules on the right side y axis, and the HRMS is actually represented here in a tabular manner, and there are different processes which are related to the electro discharge processing. So, you have ED turning, ED milling, ED boring, rimming, grinding, lapping, honing, polishing, super finishing, these are the different processes, and then you have a roughing process and a finishing process, and you can look at a comparison of these pulse energies which would be needed for creating such finishes on the surface. So, for example, rough turning produces about 100 micron HRMS, and the pulse energy which is needed for producing in an EDM 100 microns roughness is roughly about 0.9 joules. Okay. And similarly, for a finish turning operation it needs 0.8 joules. For a milling for roughness equal to a rough milling process or a rough cut for the milling process, you need typically 0.7 to 0.8 joules. So, you could actually hit upon all these process outputs in conventional systems by using different spark energies or pulse energies in a EDM surface system. What is more interesting is that if you have the pulse energy very small, you could always get in the domain between let us say 0 and 0.1, you could get into the domain of as far as 0.2 microns surface finish, although the MRR here or the material removal rate is quite insignificant, but you can actually hit upon the super finishing domain by using something like a very low pulse energy system. And so, typically in electro discharge micro machining, when we talk about really more like a surface finishing issue rather than material removal issue, we can use such low pulse energies to create surfaces equivalent to almost super finishing processes. So, that is how the HRMS in microns for all these different processes, which include rough turning or finish turning or rough milling, finish milling, boring, rimming, grinding, lapping, honing, polishing, super finishing, these different processes have been mentioned in the table here through the hashed areas. For example, rough turning would typically result in about 25 to 100 micron surface finish. These are the range in which the finishing operations happen. And on the right here, on the right y axis, it looks at some of the EDM related process parameters, particularly as a function of the pulse energy. So, you can look at the various intersections. So, this line here, dotted line, represents what is going to be the surface roughness like for a certain amount of pulse energy. Pulse energy 0.9 would result in a surface roughness which is almost same as turning rough turning, about 100 microns HRMS on the surface. So, if we look at the intersection of the hatched areas with the pulse energy, we could get the different pulse energies for which you have similar roughnesses to the processes mentioned here. For example, you could have with EDM surface roughness as good as rough milling or rough turning, or even let us say rough boring, something like that. And the finishing processes are a little far away. You can see always there is a distance between the trend, the curve and the hatched area for the different finishing processes. So, EDM really in order to fall into the finishing domain may need a little more to do in terms of pulse energy. For example, we can actually have a good amount of let us say finish turning, or which is this 12 microns, or finish milling which is about 12 microns, associated with the EDM process at extremely low pulse energy of the rate of about 0 to 0.1 joules. So, this is typically more like it is not really a material removal operation, but more like a surface finish operation. Okay. So, typically that low pulse energy of this grade about 0 to 0.1 is only done in very specific cases, particularly in micro machining, etc., using electro discharge machining. Okay. So, that is how we can correlate the conventional processes and their outputs in terms of roughnesses with respect to what the spark machining does. And as one can interpret from this curve that these low pulse energy processes, which are almost used as material finishing processes, can to some extent rhyme and rhythm with the finish turning or finish milling or finish boring, but the kind of finishing that is needed for polishing or super finishing processes can never be obtained through the pulse system in an EDM process or electro discharge machining process. So, let us look at some numerical problem designs and try to estimate through the empirical relation that had been made earlier about HRMS with respect to the MRR. It was 1.11 q to the power of 0.384 where q was in millimeters cube per minute and HRMS was in micrometers. So, that is how we were empirically relating the HRMS to the Q. We give a problem design where let us say there is a steel work piece being machined. So, the formulation that has been mentioned earlier would follow very well, and the resistance capacitance circuit for the EDM system which is actually machining on the steel work piece has a resistance of 50 ohms and capacitance of about 10 microfarads, input power supply of 200 volts, the discharge power supply of about 150 volts. So, we have to estimate what is going to be the surface roughness in this particular case. So, let us talk about the pulse energy. Okay, so, the energy actually in this case is given by half CVD square, where VD is basically the discharge voltage and C is the capacitance. So, if we look at the energy here, it is half times of 10 to the power of minus 6 times of 150 square, and that much joules, which is actually 0.113 joules, is what is needed as energy. Let us also estimate what is the cycle time, which can be approximated by looking at all these parametrics here, the resistance and capacitance. We know that the cycle time Tc of the relaxation circuit can be approximated as the resistance Rc times the capacitance, which is 10 to the power of minus 6 farads, times of log to the base e of V0 by V0 minus Vd, which is 200 by 50. Okay. So, this comes out to be about close to 710 to the power of minus 4 seconds. So, this is the cycle for really one discharge to happen, which includes the charging time in most of the case, which includes in most of the portion as the charging time and very less portion as really the discharging time. Discharging is almost treated as momentary or spontaneous. So, the average power input will then be calculated as W equal to 0.113 divided by the cycle time 7 into 10 to the power of minus 4 seconds. So, this many watts, or if I wanted to convert this into kilowatts, we just multiply that by 10 to the power of minus 3. So many kilowatts. So, this comes out to be equal to 0.16 kilowatts. And so, we use for steels the other empirical relationship we had formulated earlier for the material removal rate Q, where Q is actually related to 27.4 times of this value W to the power of 1.54, where Q is in millimeters cube per minute. Okay, and here we can have this as 27.4 times of 0.16 to the power of 1.54 millimeter cube per minute. That is how we can correlate Q. This is about 1.633 millimeter cube per minute, and with this as the new value of Q, I could be able to calculate the surface finish through the HRMS formulation for the steels. So, the surface finish in this particular case is represented by HRMS equals 1.11 q to the power of 0.384, which is 1.11 times of 1.633 to the power of 0.384, about 1.34 microns. So, the surface finish for this small a spark is roughly similar to what you get for around finish turning, or even to some extent finish boring, or probably to some extent reaming processes. So, that is how you can define surface roughness, particularly for steels while cutting it in EDM process. The other issues which are important for me to mention here about EDM are the different inaccuracies which are introduced because of the way that the EDM process happens. There are mainly 3 different inaccuracies or kind of inaccurate machining which is introduced because of the way that EDM is done. One of them is hole tapering. So, basically whenever you are doing a through drilling using an EDM using ED drill system, there is always a possibility of formation of a tapered hole. One of the reasons why that is so is very obvious, that the sides of the tool here, for example in this zone, are always exposed to creating a breakdown field and creating sparks to happen. So, not only the sparks are actually created by the face of the tool, but also the sides of the tool, which results in some kind of a tapering action. So, obviously this portion of the workpiece would be exposed to more number of sparks in comparison to this portion of the workpiece, because the tool has been inserted for a longer time there. So, obviously the erosion at this place would be much more in comparison to the erosion at this place. So, a very simple reason why there would be a self tapering of the hole, and in fact one of the ways to control is to sort of maybe introduce some insulating materials in the tool around this particular zone, so that only the face is the one which creates the breakdown and the sparking process. But again that is something that needs to be addressed by the tool designer, because not all tools are having the requisite amount of size and shape for supporting such a process of insulation. So, the second problem that exists is the overcut due to the sparks at the side faces of the electrodes. Particularly the problem comes when there is a tendency of a debris material to be caught between the side wall of the tool and the hole that is being created on the ED surface, ED machine surface. So, there is always a change in the spark length because of it, which would adversely affect the roughness, surface roughness at the side faces. Also, there are errors due to the gradual change in electrode tool shape and size. Let us look at some of these errors one by one. Taper, for example. So, as you can see here, that as the tool electrode advances, the shape of the hole machined is like a taper, okay. And taper is because the upper portion of the hole walls is always subjected to more number of sparks than the bottom portion, obviously because the tool sides are also generating sparks in comparison to the tool faces. So, you could control this by using appropriate electrical parameters and also insulation at times if you want to avoid the taper. The overcut basically is a dimension by which the hole in the workpiece would exceed the electrode size. So, magnitude of the overcut would be dependent obviously on the spark length and to some extent on the crater dimensions. This dW here, for example. Okay, so, you can see here the overcut actually is actually represented by this arrow. Okay. So, you can see that the tool diameter is always lesser in comparison to the hole diameter, obviously because there are going to be sparks from the side faces as well, the tool. So, the wear particles which are present sometimes from the debris in the gap, they create a lot more problem in terms of enhancement of the overcut size. And this phenomena is represented here, that let us suppose there is a particle from the debris, this black circle that is being represented here of diameter dW present in the gap between the tool and the workpiece. Okay. The effective length of the spark now and hence the magnitude of the overcut would be increased by the diameter dW. So, because obviously when we talk about the breakdown field or breakdown electrical field, the particle, because of being mostly of metal, or mostly because of the debris, is treated as of the same dielectric capacity as the tool or the workpiece. And so, therefore, the effective spark length that would allow this breakdown field to happen, okay. So, where the condition E, if you may recall, E applied greater than or equal to E breakdown, would necessitate at least dW increase, this is breakdown, would necessitate the increase of spark length by the amount where the medium in the spark path suddenly had same conductance to the tool or workpiece. Okay. So, that is the reason why the spark length here would actually be this plus this much, where this extra width here is equal to the dW. So, this results in even bigger overcuts and a bigger problem. So, if the debris is not flushed out properly, obviously the overcut size is going to be much more. Now, this figure right here shows a case when a 10 millimeter diameter brass tool is used for machining steels, and this shows really the taper that could be formulated by the values on the right side x axis, and the overcut that could be formulated by the values on the left side x axis as a function of the spark energy. So, you can see if the spark energy is low, the overcut also generated is low, and similarly so is the taper. Okay. But as the spark energy is increased, both the overcut and tapers are increased. So, this is only a case where there is no forced circulation mechanism and only a passive EDM operation without any dielectric being circulated going on. So, this is a major issue when we talk about EDM. So, electrodes really play a very important role in EDM operation, and therefore, we also need to look at some of the wear related characteristics of the tool electrode, because that may determine the ultimate shape and size that you are wanting to die sink on the surface through which machining is being carried out. So, if we look at that aspect, the tool electrode wear in a EDM is really because the tool gets eroded due to the sparking action itself, and the materials having good electrode wear characteristics are same as those that are generally difficult to machine. One of the principal materials used for the tooling in EDM is graphite. Because of its highly conducting nature, it goes directly into the vapor phase without melting and creating any problem like debris etc., which may result in the increased spark length or increased overcut etc. So, we look at the various tool electrodes through a parameter called wear ratio RQ, which is defined as the ratio between the material removed from the work to the material removed from the tool. So, RQ is really equal to the amount of material removed from work to same removed from tool. So, obviously, if RQ is low, amount of material removed from work is lower in comparison to the tool. So, you have to have a high RQ value for a electrode to be appropriate. Okay. So, this you can also directly relate to the ratio of the melting points of the work and the tool, and the way that the relationship goes is that our RQ really depends on the ratio of melting points of the work and tool. In this manner, RQ equal to 2.25 RQ R theta to the power of minus 2.3. R theta is melting point or melting temperature, let us say, of work by melting temperature of tool. So, that is how the RQ and R theta are posed here. Regarding electrode material, the selection of the electrode materials really depend on a lot of these parameters like MRR, wear ratio, ease of shaping of electrodes, the cost at which the electrodes are bought etc. And in fact, there is a detailed analysis about what workpiece would necessitate what electrode material and also the what dielectric material. So, in the interest of time, I will close this particular module today, but maybe in the next module we will talk a little bit about the electrode materials and dielectric fluids, and then also look at some of the different effects of EDM on surface roughness and hardness, which is a very important critical parameter behind any machining process, which happens because of this ablation because of thermal means. And with this, I would like to finish this particular module. Thank you and goodbye.